Thank you all for joining our masterclass today. My name is Dylan Kassane. I work with the marketing team here at Witekio. And along with our good friends from Mender, we're very happy to welcome you to our Yocto Masterclass Hardware and Software Variants. We've got a pretty packed agenda and a lot to get through today, but we are going to kick off with a quick introduction to our three panelists, and then I'm going to pass things over to them for a deeper dive. So let me introduce you to the experts who are going to show us the way today. First up, let me welcome Joseph Holzmeier, Head of Developer Relations at Mender. Joseph, can you start by telling the audience just who you are and a little about Mender as well?
Hello, everybody, from my side too. Well, as already pointed out, I'm Head of Developer Relations at Mender.io. We do provide over-the-air update solutions, and well, I'm been in industrial controls for like 15 years by now. I grew into the Yocto project for a real long time, and finally I became an ambassador. So it's a pleasure to speak upon one of my absolute favorite topics to you all.
Fantastic. And it's good to have you here, Joseph. Can you tell us a little bit about Mender just before we jump in with the other two gentlemen?
Well, Mender is one of, or the leading solution for over-the-air updates to connected devices, specifically Linux devices, where we enable you to seamlessly deploy both system and application updates in a really robust and comfortable way. And we provide both the integration on the device as well as the backend that you can interact with.
Fantastic. Also joining us here today from Witekio is our first of two guests. Nick Elsmore is one of our embedded software engineers. Nick, it's great to have you here. Can you introduce yourself and tell us a little bit about Witekio as well?
Sure. So yeah, thanks, Dylan. My name is Nick Elsmore. I've been a firmware and embedded engineer for about 6 years now. 3 of those have been at Witekio. Witekio is a company that we help provide software solutions to our customers, BSPs, cloud, application level work, really everything that the customer may need to get their product out.
Fantastic. And also joining us from Witekio, another embedded software engineer, Florian Rebo. Florian, introduce yourself.
Hey, so my name is Florian Ribaudo. I've been working at Witekio for the past 4 years, and I've been working on embedded software, especially Linux, for the past 7 years.
Fantastic. And of course, along with our 3 guests here, it's great to have you, our audience here. If you have any questions during the webinar, please add them using the button at the bottom of the window. We're going to try and get through as many as we can in a Q&A session at the end there. But to get us underway, I'm going to hand over to Nick to get things started. Nick, kick our masterclass off.
Sure. Thanks, Dylan, and thanks everyone for coming out and hearing us speak today. Today we'll be talking about Yocto and specifically how to manage multiple hardware and software variants. We'll get into that a little bit later. And then after that, Joseph will be giving us some instruction on Mender, specifically with regards to Yocto. So to start off, I'll be talking about just Witekio's background with Yocto, and then I'll dive into, basic what is Yocto, a little overview, and then I'll pass the torch on to Florian, and he'll go into some details and teach you how to create your own custom distribution with Yocto, supporting multiple boards or multiple images. So at Witekio, we know that developing a BSP can kind of be a blocker. It's not necessarily the most interesting part. When it comes to developing your product, you're mostly focused on the application. So we've developed Avnet Embedded BSP to really help accelerate your time to market, so you can get started on your application right away. You actually don't even need hardware. You can start developing just in an embedded or a virtual environment. We also offer a lot of SOM flexibility. Our BSP supports a number of different SMARC modules, Avnet embedded SMARC modules right away out of the box. And you can actually just switch between those different modules without much effort at all. So this really allows you to scale up and scale out. You can just switch to the next SOM without changing much at all in your BSP or your application. And the way that we do this is we introduce an abstraction layer. So this abstraction layer sits on top of the BSP, and your custom application will be written just to speak with that abstraction layer. So you won't really even need to know much about the BSP at all when developing your application. Now, Avnet Embedded BSP hasn't quite been released yet, but if you want to know more, or you're interested in our early adopters program, go ahead and talk to us after the webinar, and we can start talking about that. So the way that we built Avnet Embedded BSP is using Yocto. So what is Yocto? Yocto is it's an open source build system. It's based on Open Embedded, and it's very useful for creating and managing custom embedded Linux distributions. It contains a number of powerful tools, giving it a lot of flexibility, and it makes it very useful for the developer to manipulate and extend and very well define their BSP. It's maintained mostly by the community. There's thousands of packages out there that are available, offering a lot of flexibility and really accelerating the development of your BSP. So at the core, Yocto is built up of recipes. And recipes are used to define different software components. These could be tools, dependencies, libraries. You would write a recipe for your application to build your application. And then finally, the recipe is going to define your final image. And these recipes are going to contain the necessary information for fetching it from its remote, wherever it lives, configuring it, building it, and how to install it on the target. You also will be defining various machines. These are going to define the target hardware that these software components and your final BSP are going to run on, various features that they support, how they're configured, etc. You can also define distributions, and these are going to this is going to define your cross-package configurations, compile time options, etc. And all of these configurations and recipes are going to be bundled up into meta layers. And so here's the basic structure of a Yocto project, basically. You have a number of different layers. Some of these may be maintained by the community. Some of them may be maintained by the SOC manufacturer or some other vendor. And then at least one of them is going to be maintained by you. And that's going to basically define your distribution. And I'll pass the torch on to Flo, and he's going to go into some more detail about this.
Hey, everybody. Thank you, Nick. Thank you for the high-level explanation of what is Yocto. So now we're going to dive a little bit into how to create your custom distribution in Yocto. So first, Nick was telling us about the meta layers. So what are they? Basically, they are Git repositories with instructions on how to build different packages, and in the type of instruction that you can find on how to build packages, like the Git repository where the package is maintained, the version of the package, how to configure it, the licensing information. So some of these layers are maintained by the community. So for example, if you're working with an NXP product, you're going to use the Meta Freescale. If you want to build a Yocto for the Raspberry Pi, you can use the Raspberry Pi meta layer. If you want to use the OTA update, you can use the Meta Mender. And there are so many metas maintained by the community. It's sometimes hard to find the package you want. And you can use this website to help you find the package you need. Also, you're going to want to create your custom meta layer to add your own application to your BSP. Or if you want to update what's been done by the community, you can also do it. And then you have to create your custom images. So for example, here at Witekio, we often create a production image that contains the bare minimum to get your application running, and also a development image that contains the production image plus some development tools. So what does a meta layer look like? So on the left here, you can see that the meta custom contains one conf folder that's going to contain the configuration of your layer plus the definition of your machine and the definition of your distribution. We're going to dive into them in a little bit. Also, you're going to have in the recipes, for example, an update of the BusyBox and your own customer application. So if you look at the image on the right, you see 3 different layers that are interacting with each other, and each layer has a priority. So the higher the number, the higher the priorities. For example, here, layer 1 and layer 2 are maintained by the community, and you are layer 3. So what you can do is append the layer. So in layer 2, this BB file is not exactly what you want, so you can modify it using a BB append. If 2 files have the same name in 2 different layers, the higher the priority, Yocto is going to choose to install this file in your image. You can also just choose to pick a file from a layer without modifying it. So that's basically how different layers interact with each other in Yocto. So how do you configure a layer? So first, in the conf folder I was telling you about, in the bblayers.conf, you're gonna say, okay, my layer needs all these layers underneath to function. And you will also have to configure the priority of your layer. So usually it's gonna be the highest because you want everything in your layer to be in your image. And then you're gonna add all the recipes that you created inside of your layer to tell Yocto, okay, if you're looking for this package, you can look here as well. And then how do you create a custom image? So custom image lists all the recipes you want to install on the target. And you can also choose the image type that you want your image to be. So for example, X4 or X4.gz, they're very good for production images. tar.gz is good for development purposes because you can easily uncompress it and modify the folders inside and see what's been installed in the image. And the wiki image is also very good for production images. Then you can create multiple images. For example, here, a production image or a dev image, or both. So how do you create a custom image? So for example, for the production image, as I said, you want the bare minimal to get your application running. So you're going to want U-boot, Linux. If you have a Qt application, you're going to need the Qt libraries. If you have a Wi-Fi connection, you might want WPA supplicant. And for example, here the file system, the image type is x4.gz. Yocto also provides you with a BB class core image that's going to help you create the bare minimal because there are much more to it. This is just a small example to create an image. And then in your development image, you're going to want it to be based on your production image and then add a few features to it. So for example, the debug tweaks that are going to improve, like for example, remove the root password, which is convenient when you're developing. You might want to use lsblk. That's not needed in the production image, but good for debugging. Same for OpenSSH. And you might also want to build it as a tar.gz for debugging purposes. Now that you've created your image, you're going to want to create your machine. So what's a machine? A machine basically describes the target hardware. So a lot of machines are maintained by the community. So for example, in Freescale, you can use these files to create your IMX machine, or you can use MetaIntel to create your Intel Core i7 machine. But these are the basics for the SoC. But in your case, you might want to, for example, update the serial console, and that's how you do it. Add some features that might not be in the base machines. So for example, Wi-Fi and Bluetooth. And also you're gonna want to select the device trees you want to build with your kernel. And so now you've created the image, the machine, you need to create the distribution. So the distribution is going to describe the BSP capabilities. There is one distribution called Pocky that's maintained by Open Embedded and comes with Yocto, which is very convenient for debugging because it adds a lot of features, like for example, ALSA, Bluetooth, that you might not need, but for debugging purposes, you know, this distribution works, so it can get you going. And then you might want to create a custom distro to fit your needs. You can have more control over it, and it also reduces the image size. So how do you create a custom distribution? So you just give it a name, and then small description. You can also give it a version. And when you build the image, you can also add -- the name of the distribution after the name of the image to help you find which image was built with which distro. Same as the machine, you can add some features for the distribution. So for example, if you had Bluetooth, when you build Qt, it might look for this feature and it's going to configure the package a little bit differently because in the distro features, there's Bluetooth or maybe Wi-Fi. You can also change the init manager. So you can use systemd or create another distribution with the exact same packages, but this time you're going to use sysvinit. So now, how do you support multiple boards with your Yocto? So basically the answer is you create different machines and you build the exact same BSP, but with different machines. So inside your meta layer in the configuration folder /machines, you can create your different machines. If they're based on the same SoC, for example, the IMX8, you can factorize the code and create an include file to put everything that's the same for every machine. So how do you support multiple machines with your port distribution? So you might want to apply some patches for one machine, but not for another. So basically in your app, you're gonna create in the recipe for your app, you're gonna create a subfolder called file and a subfolder with the name of your machine and the different patches you want to apply depending on the machine. Also, depending on the machine, you might want to fetch a different U-boot and a different kernel. And this will be done using the preferred provider variable in Yocto. And you can also, depending on the machine, fetch a different version of the U-boot or the kernel or whatever. And this will be done using the preferred version variable. So now you have multiple, the same version for multiple boards. And if for one board you want multiple version, you're going to want to create multiple images or create a new distribution. So how do you do the difference? Basically, if you just want to add packages, like the difference between the prod image and the development image, you're going to create a new image. But if your distribution has new features like Bluetooth and Wi-Fi, you might want to create a new distribution instead of creating a new image. How do you configure your build? So in the meta layer, in the conf folder, in local.conf, you're going to set the default values of your machine and your distro. And then there's a little thing that you can do if you want to reduce the size of your Yocto once it's built, is inherit the RM work, which is going to remove the sources and just leave you with the binary. So how do you build now? So first of all, you tell your Yocto that you're going to use the configuration in your conf folder of the meta custom. Then you can select your machine either by leaving the one that's in the default values that we set earlier, or you can export a variable in bash and override the distro and the machine value. And then you build your image, so bitbake, and then the name of the image. So prod image, dev image, custom variant 1, custom variant 2, whatever. And now that you've built everything, where do you find the artifacts? So everything is going to be in a Yocto is going to create a build folder, and you're going to find the sources and what Yocto's fetched and Yocto logs in tmp/work. And the final images will be in build, deploy images, and the name of your machine. So if you build the same BSP with different machines, that's where you're going to find all your images. You can also find the artifacts. So for example, you can find the U-boot binary, you can find Linux Z image, you can find the DTBs that have been built there as well.
All right, thanks, Florian. So just to sum up everything that we talked about, so Yocto, first and foremost, is a build system. It's useful for defining and creating your own custom embedded Linux images and distributions. Using Yocto, you can use one code base, so one project, and you can maintain really everything that you need to. You can maintain multiple target hardware, multiple target software variants. If you're running the same image on multiple devices or different images on the same device, you can manage all of that within the same project. If you want to learn more with us, we offer customer trainings. You can just get a hold of us through our website, or you can also contact us if you're interested about the early adoption program for ABNet Embedded BSP. So thank you very much, and Dylan, I'll hand it back to you.
Perfect. Thanks, Nick, and thanks, Florian, as well. Just jumping in for a second to say, look, we are running into some scaling problems here. We've hit a couple of limits on the number of people who can be in the webinar. There's a lot of you in the webinar right now, and unfortunately, some of your colleagues haven't been able to log on. We apologize for that, but we will be sending a recording out afterwards, and they'll most certainly receive that after the event today. If you've got questions for Nick or Florian, or certainly for Joseph afterwards, do add them into that Q&A box. We'll get to as many of those as we can shortly, but let's keep going. Let's keep moving forward for the second part of our masterclass. Joseph, it's over to you.
Well, thanks, Nick and Florian, for getting us started. So here it comes. Okay, so now we've talked a real lot about the ins and outs of Yocto and metadata organization. And to get back to Mender, and with Mender we mean updates, we need to put that aside for a little moment and talk about what updates actually mean in a Yocto and embedded context. Unlike updates for desktop distributions, you have a really different set of challenges and things that you want to put marks on your checklist in order to fulfill them. And the first thing really is it never should render your update unusable, even when something happens during the update, like losing power, losing connectivity, whatever, because after that, the device will be as useful as a brick, and we call it bricked. This is totally not acceptable. Along the same lines, go atomic updates. You always want an update to be deployed completely or not at all. This comes in the application or in the deployment of the update, but also in the update artifact that gets deployed. This should be integrity verified, and if you are deploying to a device that is not meant to run user-supplied code, you might also want to employ code signing so nobody else can inject updates and modify your device's operation. How does Mender actually fulfill those needs? The key here is using AB system updates. And with AB, we mean 2 partitions for the system. And as you can already see from the graphic, there's a little bit more to that, which we will need in just a moment. So let's just go through it real quickly. On the left-hand side, you see the graphic with the 4 partitions or 4 boxes on the device. Those are the bootloader, the A and B partitions, and the persistent data. For the moment, it's just important to understand that there are at least 4 of those in a full, this is the keyword, in a full device software setup. From that, we go to the A and B partitions. A/B system updates work like this. Whenever a system is actually operating, it obviously uses some set of software. And the set of software that it uses is called active. This is the software that is actually just running the device. And in an A/B scheme, you have a duplicate set of software of which one is always inactive. So when an update gets deployed, the system running on the active partition puts the incoming update on the inactive partition. When it is finished, it sets a marker for the bootloader in order to notify it, hello, update has arrived. Then it reboots, and the bootloader, using that marker, knows, okay, now it's time to use the inactive partition and make it active. It boots up, and if everything works fine, then the application on the now active partition arrives at the working state, notifies the bootloader again, and says, yes, update was successful. And then the switch between active and inactive is made permanent. It is committed. If something goes wrong during that process, then like the system reboots before it hits that confirmation stage, this can happen because of a watchdog applying, because of a crash in your application, whatever. Then it reboots. The bootloader realizes, oh, there is another reboot now, but this confirmation has not been set. The update has obviously failed. I'm rolling back to the last known good active. So this is the core functionality here. You see, we need actually like two things taken away from this slide. And in one point in time, we need the full image that sets up all of the partition table and setup on the device. Bootloader A, B. Persistent, you can add others as your application requires, but that's not necessary. And we need another form of artifact that only brings the payload for the system that goes into either the A or the B partition. So this we call a system update. Just to distinguish them properly, when you're using Mender, then the full images usually either bear the .st image or the .uefi image suffix, whereas a system image that only goes for the file system inside, that usually goes by .mender. And what is important about the .mender files, they do not change the persistent data. The persistent data partition is where you keep your invariant state of the device. Now we have two things that we need on a specific device. Follow me along. We are going to more hardware variants, the topic that Nick already introduced us to. For each of the hardware variants that we want to manufacture, we obviously need the initial system image that sets up all of the device tables. So for n hardware variants, we need at least n full builds. Now we have shipped all of those devices and we want to roll out updates. That means now we need system images for each and every hardware variant in the field again. And for those of you who are experienced in actually manufacturing hardware, you often even have more devices in the field, more hardware variants in the field than you are actually manufacturing at the moment. So it is at least another times n images. So you see this grows. And once you have all those images and they are on the devices, they are on your update generating feed, it is absolutely crucial that you never mix the combinations up. Because imagine that you have a device running on hardware variant 3, and then you deploy a system update for hardware variant 5. This is like a couple of megabytes at least. And your customers are usually neither happy if the device is bricked because an incompatible hardware update is being deployed, nor if they have to pay a lot for a connectivity if they are on a thin mobile connection or whatever, where they have to pay by the megabyte. So matching system updates to actually running software distributions is absolutely crucial in a proper update solution. And this is what Mender actually takes care of. So we are building for multiple hardware platforms. Nick and Florian already introduced the concept of a BSP, a board support package, and we need to go a little bit more into detail here, because a board support package in the Yocto sense has a couple of things that it should do and that it should not do, or rather must not do. And you will see in a moment why that is. A BSP should do everything that you need in order to make a specific set of hardware work. It should bring a compatible bootloader. It should bring the kernel that you need in order to make the device work. If needed, it brings additional drivers or firmware blobs if it's really some crazy stuff, and in many cases also configuration. These are the things that whenever you build for a specific machine, the BSP shall give you those. The keyword is when you build for a specific machine, because if you're not building for that specific machine, it's absolutely essential that the BSP does nothing, that it does not affect your build at all. And this is the key, because once you have that in place, you can add multiple BSPs into a singular build. This is perfectly fine, and it's an explicitly supported use case to add in like a Freescale BSP, to add in a TI BSP, to add in an Intel BSP. If the manufacturers of your boards did a good job, then they will not clash. I have linked the best practices document by the Yocto project for you to revisit that. So we are coming really close to where everything falls into place in the big puzzle. We have already talked that a BSP brings things into the build. And this is usually the machine configuration, because the machine defines a real lot that goes into all of the build, just like the instruction set architecture. Every package has to know if you're building for x86 or if you're building for ARM. This usually comes from the machine configuration. Then there's the distro configuration. The distro configuration should be kind of orthogonal to the machine, because it defines the API that you are going to be able to use in your application that you are going to run on the device. So whatever you intend to use in form of software, or the kind you intend to use it, this should all be defined in the distro. Hint, using Mender essentially defines the behavior of your distribution. So this is one thing that usually goes into a distro configuration. The image recipe that Nick and Florian already touched upon then define what the application pulls into the building on top of the distribution. So the image recipe is actually the only place where you should create like a dependency tree, whatever goes into the finally created image. And then, last but not least, the already mentioned local configuration, the local.conf. This should be really treated as transient. It does not go into any kind of revision control. In many cases, it is automatically created in the build setup, in the CI pipeline. So this should really only bring the things that are relevant for this one specific build run. We're getting really close. In a Yocto build, everything that is a configuration is global. Everything that is a recipe is local. So recipes cannot affect each other. That's really one of the core key takeaways if you ever work on anything Yocto. So when we're talking about the things that we do here at the moment, we care about configuration. And now we're going to put everything together into our machine configuration. This is also the thing that Mender will use to match your system update versus your already existing full image. The machine must match. So if you're sure that that you've built for the same machine configuration, then everything will be happy. For Mender, you probably might need to add some minor additional information to the machine, like how big the boot partition is. But you should not modify your board vendor's BSP, because then you end up with a lot of headaches when a new release comes in. Into the distro configuration, there goes obviously the Mender integration. And we are talking about specific updates that get released out, like release 1, release A, release super fantastic. This is something that should go into the local configuration, because you will only do this once in a transient, meaning you will build the artifact exactly one time, then it goes out, then this build is done. Next release is coming up. So exemplary for the machine configuration, but the exactly same concept applies to the distro. The trick is to have your own application layer that pulls in overrides that tie everything together. This is an example for a machine override. For example, one of our machine or our hardware variants is the BeagleBone Black, and I need to add 1 or 2 variables in order to make Mender work on it. I come up with a fancy name for it. I went with mm-bbb for Mender multi BeagleBone Black, and I created my own layer. And on the conf machine, this is the canonical path, I drop my new machine configuration. That file name defines the final name of the machine. And here comes the trick. I just define this machine overrides BeagleBone Yocto. This tells all recipes, okay, you can behave like this was a BeagleBone. And then I pull in the original machine configuration. Now I have a perfect clone of the BeagleBone Black that serves on the original, but I can override stuff because Yocto always parses metadata from top to bottom. So at the line, your stuff here, I can do whatever I want. I can add whatever I need for Mender, and it will not affect the original BSP while it keeps me, while it enables me to put everything under my own revision control. Whenever I do such things, I usually advise to explicitly disable machine, so I'm really sure for whatever I build when I do this. Now I have repeated the step I just told you for a number of times, n, for all my hardware variants, and I can build now. I set up only one build directory, and then I go like machine equals mm-bbb bitbake my image. I have another one. I call it machine mm-raspberry bitbake go. And this will not clash in one build directory. All artifacts, especially the Yocto internal ones, will be reused as much as possible, especially native build artifacts, whereas everything that is not hardware independent will be perfectly separated under the deploy. Conclusion, when you do this, you get super coherent states, coherent builds for both your system images as well as the full builds. Plus, it is perfectly suited for code rebuilds in your CI/CD pipeline setup. And if you trimmed or if you collect all of your machine and distro information in your additional layer, then it is super easy for you to version control this. With that, if you ever want to know more about Mender, which hopefully is right after this presentation, just get in touch with us, shoot me a mail, check out the hub, check us out on GitHub, get in touch, tell us what you want, tell us what you need. We will see how we can help you. And with that, I hand it off again to Dylan for the questions. Thank you.
Fantastic. Thanks, Joseph. And thanks for the questions that have already come in. We've got a bunch of them, and I'm going to jump straight into the Q&A so we can address as many of them as we can. Rest assured, if we don't get to your question, we'll follow up and answer that by email afterwards, but let's see how many we can get through now. Nick, I'm going to shoot the first one your way, maybe at a higher level here. What branch of Yocto should I use? Do specific branches have features that other branches don't?
Yeah, so the branch that you're going to want to choose is typically going to depend on what your target SOC or other community layers you're trying to integrate are. The layers provided by the community don't always support each branch, so you're going to want to try and find the branches that are supported by the various layers that you're trying to use, and try and find something that matches up.
Fantastic. This one may be for you, Florian. Is it possible to support parallel bitbake processes building against the same image type, but slightly different recipes, and having all these build processes sharing the same TMP dir, DL dir, and TMP dir? Of course, we only changed the deploy dir to have builds locally for each build.
So I've actually never run bitbake in parallel on the same image. I'm not sure it works, but what I would recommend to speed up the build is look into the state dir, and you can share it between different builds. So Yocto is gonna like look into these state, see what's the same, see what has changed, and only rebuild what you need if you build for a different machine.
Joseph, did you want to jump in there as well?
I would be a bit nitpicky on that, on the wording of the question, because parallel might mean actually in two different shells, and that is explicitly not allowed. Whereas having a shared estate served out via NFS, HTTP, whatever, there are a number of protocols supported, that specifically is allowed.
Okay. Joseph, I'm going to point this one to you as well. From my understanding, Mender will support 2 partitions. If we're using a different architecture and we have 3 partitions, so OpenSBI, U-boot, kernel, and rootfs, how does it work for 3 partitions?
I'm not particularly sure that I understand the question, but let me word it like that. You have one partition where U-boot and SPI and or OpenSBI and all of those things reside, and that is essentially the bootloader partition. And this is the one that was right at the top of the graphic. So yeah, Mender usually uses at least 4 partitions because you will want to store your persistent data somewhere. And if we're going back to that, then I do not exactly see where it is different from a standard setup, because you have 2 payload partitions, one U-boot partition. It's just like a standard setup. But if I got it wrong, then just shoot us a mail to the address in the slides, and we will clear it up.
And of course, we will be sharing the slides with everyone as well. Another one for you, Joseph. Does Mender support allowing installing third-party applications on a running image, ideally with some sort of certificate validation?
Yes, that one is really simple, because that is called an update module. We have already update modules for just simple files, for Docker containers, and you can create arbitrary complex additional update modules. So that's a clear yes. It depends only on your use case and your imagination.
Okay, Nick and Florian, this one came in quite early, and we answered it in the chat, but I think it's important to touch on as well. How do you find out what my serial device is without booting up the device? Is there any way to find that from the source? Different boards have different device names. Who can jump in there?
Yeah, I can help answer that one. And I think Joseph answered that inline too, but I'll reiterate some of that.
Sorry for that.
Oh no, that's okay. Yeah, I basically have the same thing to say. It's going to be hardware dependent. You're going to have to. It's one of the more annoying things when working with Linux, but you're going to have to look at both the reference manual and the device tree to determine which one is going to be enumerated first. But typically, if you follow the device tree, that should work.
Okay. Joseph, is it possible to update the bootloader with Mender?
It is. It's just not there in the default because we try to keep the bootloader as slim as possible. But it is possible. It's just another use case for an update module in the end. And if you're interested in that, I invite you to both join Embedded World, where a colleague of mine will be speaking on that, as well as the Building IoT conference. It's German in Karlsruhe in May, where I will be speaking on that specific topic. So again, clear yes.
One for you, Florian. What's the best way for someone to actually reach out to yourself or to Nick at Witekio? Where would you point them?
So you can directly shoot us an email. It's the first letter of our first name and then our full name, all attached, at witekio.com.
Okay, and if anyone's got any qualms about the spelling there, you can probably also reach out through the website as well, yeah, and through the contact form, and we can forward it on to the guys. Joseph, what differentiates Mender from, for example, RAUC?
I think the most striking difference is that Mender is an integrated solution, which brings both a backend that we also host, or that you can self-host if you desire so, and a client, whereas RAUC or RAUC is essentially only the client on the device, and it always relies on an additional deployment server like Hawkbit if you want to have a comparable experience. It has also upsides and downsides. I would say it's a very good solution if it fits your use case. They have some features that might be useful for you that we do not explicitly support in order to provide best in breed for the situations that we deem more important for the majority of users. And first and foremost, the full solution approach, because Rockbit means you have to take care of two components. Mender means you have to take care of one.
Okay, a question here from Andreas for you as well, Joseph. How do you define the conditions to determine if the update was fine?
Usually it is device boots back up again, then connects to the backend and defines has been fine. Let me read the question.
Yeah,
just for it.
Essentially, here it's imagine it.
Yes.
Imagine it's booting up. It can't connect to the cloud anymore. Is that going to trigger that fallback?
I'm not sure if it triggers it by default. If that is of relevance to you, ping me by email or on the hub, and I will look into it. You can at least define it the way if it is relevant for you. So it can be done. I'm just not sure if it is the default.
Okay. William has a specific question on Mender there. Is it possible for Mender to not update, so not push that update unless the client or customer specifically requests to download the update? And the example there being on something like iOS, where a user can decide.
I love questions that I can answer with a straight yes. Okay, so it is again not the default, but the Mender client has an API that is exposed over dbus, where you can essentially implement whatever behavior you want to. So yes, this is supported. Yes, this is a use case that quite a number of our customers have. Think systems that are remote, systems that are safety critical. So yes, it's possible. Yes, it's supported. Yes, we know about it. We got you covered.
Nick, I'll point this one to you. Is Full Metal Update still actively supported?
That's actually a great question, and I don't know. I'll have to go and ask. Florian, do you know?
No, I don't know. I've used it in the past 6 months, the past year maybe, but I don't know if it's actively supported.
Yeah, I haven't been a part of that project for over a year, so I'll have to ask. But yeah, if you can, Dylan, do you think you could write that down and we can contact them afterwards?
Yeah, for sure. So Marco will definitely reach out to you with an answer to that question.
Thank you.
I love the software title. That's awesome.
Full Metal Update. It is. Yes. It is, and let's hope that that nobody from sues us, right? So sometimes we want to update an application instead of the full system to save on bandwidth. Does Mender support that?
Yes, just another update module. It only depends on how your application looks like. If it's a statically compiled binary, it's just as simple as dropping a simple file on your target. We got an update module for that right out of the box. You can deploy Docker containers. You can deploy essentially arbitrary kinds of application updates on top of your full system. Clear yes again.
Okay. Another question that we got in by email just before the event kicked off here. Does Mender integration vary across, to a large extent, across hardware variants?
I'm not. Did I get the word? Does it extend to a logic difference or large extent?
Large extent. Does it vary to a large extent across different hardware variants?
It depends on how peculiar the specific hardware is. So in terms of the BBB that I used as an example, it's just dropping in inherit Mender full into your distribution and you're all set. And for many kinds of hardware, that is actually enough, depending on your bootloader, if it's heavily vendor patched, if your kernel needs heavy patching, things like that. It might become a little bit, let's say, more demanding to set up. But all in all, for platforms that are not too crazy, it does not vary that much.
Okay. How do you scale the Mender client integration at large scale in manufacturing?
As far as I know, and in that specific case, I beg your pardon as the more like hackish guy. I usually deploy not to tens of thousands and hundreds of Ks, but we have something that's called MTLS ambassador for that, and to my understanding, this enables you to pre-authenticate devices in your manufacturing runs. So this is the one kind, and the other one is that since the newest release, we have an Azure IoT integration, which also should help you with that. If you need additional details, I will happily dig them up for you. But I'm admittedly a little bit flaky on the super large scale things.
Okay. Florian, I think this one might be for you. Is there an easy example to start from for a simple Raspberry Pi deployment with a Docker container, some device-specific configs?
That's a very good question. We actually do this. That's actually what we do with what Nick told us about. where we have the abstraction layer and we deploy the applications are actually containerized and built with Yocto. So if you want to enroll for the pre-visualization for that, this would be a good example. But for the Raspberry Pi platform, I don't know if there are any good examples.
Okay. Nick, I might throw this one to you. How many developers do you recommend to work on the Yocto or custom OS when using a custom BSP?
Well, that definitely depends on how complicated or special your BSP is, but usually 1 or 2 is enough. If you're building off of what a SOC manufacturer or a vendor has provided. If you're building one from scratch and you are the SOC manufacturer or the vendor, you're going to need more than that. But typically 1 or 2 is enough.
Okay. Joseph, a pretty specific question here. When we push that update, can a partition size change after deploying a device? For example, you ship a device with a 2 gig data partition. We find out that we need 4 gig. Can we push that as an update, or will it just brick the device?
It is probably possible. This is what again would fall into an update module, but this is something that would need careful hand carving, because data partition enlargement is not the problem. This is trivial. But usually when you are talking about embedded hardware, then your partition tables are using up all of the storage, which means that those 2 additional gigabytes will have to come from somewhere, and that usually means that you have to shrink something, and this will probably give you headaches. So I would say it's not impossible, but this is not for the faint at heart.
Okay, and I think we've probably got time for one more question, and so I'm going to shoot that back to you as well, Joseph. What is the recommended way to keep the network settings after an update?
To move the network settings to data, to the partition, to the persistent partition. Simple as that. We have an example for that, I think, on the Mender Hub that uses systemd and WPA applicant. But the technique basically should apply to any kind of network configuration that you want. This is a request that I've heard a number of times already, and be sure that there will be more concise documentation on how to do this in a producible manner real soon.
Thanks, Joseph. Look, we're coming right up on time, and I'm aware that for some of you the day is just getting started, for others the day is just finishing. So we're going to have to finish up, but I do want to thank our guests, Joseph from Mender and Nick and Florian, both from Witekio. We'll be reaching out in the next day or so with a link to the replay of the webinar, so you can watch that video again and see the answers to those questions, especially if you were asking them one more time. We'll also send out a link to the slide deck, and of course you can pass the link to the replay as well as the slide deck around to your colleagues who maybe couldn't be here or were unfortunately locked out when we hit that software limit a little bit earlier. But do share it around. We'd love to get your feedback. Of course, if you want to contact Joseph or Nick or Florian, we'll have their contact details in there as well. Or you can reach out to the Mender website or to the Witekio website, and someone will certainly point you in the right direction. Thank you for joining us tonight. Thank you for joining us today. And we hope to see you again at another Witekio event. Have a good day.